Today we will be discussing about other type of class A power amplifier, which is transformer couple class A power amplifier. So in the last class we discussed about the one type of class A power amplifier, which was series fed, and today we will be discussing transformer couple large signal power amplifier. So the transformer coupling, as the name suggests, there will be a transformer which will be used for coupling the load to the amplifier. Here let us consider a resistive load. For example, when we have to use an audio power amplifier, we have to drive a loudspeaker, for example. So we have to transfer power to a load of having resistance around 5 to 15 ohm. So this resistance is very small, but here we are transferring power from the large signal amplifier using a transistor, and as we know, the output resistance of a transistor is quite high. So here, to transfer power from a device having high resistance to a load having very low resistance, that mismatching of the impedance causes lesser transfer of power, because as the load is having a very small resistance and the device, that is a transistor amplifier, is having a high resistance, so it cannot transfer the whole amount of power because of mismatch in the impedances. And as we know from maximum power transfer theorem, if the load resistance as well as the resistance of the device from where we are transferring the power, these two impedances match, that is ideally when they are equal, that is source resistance and load resistance are equal, then maximum power can be transferred. So here, in view of that, we are going to use a transformer at the output side, that is we are going to couple the load to the device or the amplifier through a transformer. So that type of circuit is shown here, where we are having a transformer having the turns ratio between the primary winding and the secondary winding N1 is to N2. So a transformer, as we know, has two windings, one is the primary winding, one is the secondary winding, and the primary winding is where we connect the supply, and by induction we get an induced voltage in the secondary side. So here we are showing a transformer having number of turns in the primary N1 and number of turns in the secondary N2. So N1 is to N2 is the turns ratio. Now the resistance RL is the load resistance which is connected across the secondary of the transformer, and we are using a fixed bias scheme given by this resistance RB, that we similar to that we discussed earlier in series fed class A power amplifier. Here the primary is having voltage V1 and the secondary of the transformer is having the voltage V2. Now, as I have mentioned, this is to transfer maximum amount of power to the load having a low impedance. For example, in a loudspeaker where the voice coil impedance is only around 5 to 15 ohm. But the transistor output resistance used in the large signal amplifier is quite high, that is much higher than the loudspeaker voice coil impedance. So, we have to go through a transformer coupling. Now, in this transformer, as I have noted, N1 is the number of turns in the primary winding and N2 is the number of turns in the secondary winding. So, the ratio between N1 and N2 is given by turns ratio and it is denoted by a small letter n, and that is equal to V1 by V2. That is, the ratio between the windings of the primary and secondary determines at what ratio the supply voltage will be transferred to the secondary winding side. So, V1 is to V2 is given by that turns ratio n, and that turns ratio n is actually 1 by k, where k is the transformation ratio. That k, which is transformation ratio, is one term that is used in transformer to denote about the ratio between V2 and V1. So, actually k is the transformation ratio is V2 by V1. So, it is equal to 1 by n. So, transformation ratio is 1 by turns ratio, and assuming ideal transformer where the input power and output power are equal, V1 I1 is equal to V2 I2, that is the assumption we will be using for ideal transformer, and from that we can get that V1 by I1 is equal to that right side also, if we divide by I1 square, that means both left hand side and right hand side, if we divide by I1 square, what we get, V1 by I1 equal to V2 I2 by I1 square. That can be written as V2 I2 by I2 square by n square, because from V1 I1 is equal to V2 I2, we get that V1 by V2 equal to I2 by I1, and so as V1 by V2 is equal to n, that is equal to I2 by I1 equal to n. So, we can write I1 as I2 by n. So, using that relation here, in place of I1 we are substituting I2 by n, and as it is square, so we get I2 square by n square. So, this n square will be coming to the numerator. If we simplify, it will be equal to n square into this 1 I2 will cancel with 1 I2. So, what will be remaining is n square into V2 by I2. Now, if we look into this expression, that V1 by I1 equal to n square into V2 by I2. Now, V1 by I1 means the resistance in the primary side. If we look, the resistance which will be obtained in the primary side, which is nothing but the resistance RL transferred to the primary side. That means, if we imagine that the resistance which is actually in the secondary winding, that is RL, if we transfer this resistance from the secondary to the primary side, then we get the value as RL dash, which is equal to n square into RL. So, the value of the resistance in the secondary winding, that has to be multiplied by square of the turns ratio, so that we can transfer that secondary winding load resistance RL to the primary side, and that value is denoted by RL dash. So, it is equivalently expressing that we are having in the transformer primary a resistance RL dash, which is nothing but the secondary resistance or load resistance transferred to the primary side. Now, this is done in order to easily draw the load line which will be required in the further analysis, because it is a transistor which is being employed for this power amplifier or large signal amplifier. So, we will be finding out the efficiency, that means the ratio between the output AC power to the input DC power, and that requires the currents and voltages in the AC as well as the DC conditions, and we have to draw load line for the transistor to see how the signal changes. So, if we now consider the load line for this transistor, then we have two load lines. One is the DC load line, which is the load line for the prevailing DC conditions, and under DC condition we will not be having the RL dash, because the RL dash, that is the load resistance transferred from the secondary to the primary side, will be only effective when we consider AC power, because the load RL dash or RL is getting AC power. We are concerned about the AC power being transferred to the transformer secondary side load. So, if we consider the DC load line, we can draw the DC load line by noting down the maximum value of the DC collector current and the maximum value of the DC voltage. So, now if we look into the circuit again, when the DC condition prevails, if we are only interested in the DC condition, then in this circuit, if we consider from VCC to ground, this transformer primary is having a very negligible resistance. It can be almost assumed to be 0. That is, the transformer primary winding is having almost 0 resistance. That is why in this part the current, the DC current which will be flowing will be having no resistance, and that is why the current which will be flowing is almost infinite. That is, the current which will be flowing, that is almost, it will be like a short circuit current. If we consider this collector current, then as there is no resistance, the current will be almost infinite, and the voltage is VCC. So, collector to emitter, if we consider, because we have to know the maximum values of the collector to emitter voltage and the maximum value of the collector current to draw the DC load line, and that is why if we now consider this circuit in the collector side of the transistor, VCE maximum value can be the value which is the supply voltage VCC. So, under DC conditions, the maximum collector to emitter voltage will be VCC and maximum collector current will be infinite. It is infinitely large. So, the DC load line, if we draw, it is almost like a vertical line, that is because current is reaching around infinite value and the collector to emitter voltage under DC is VCC. So, joining 2 points, actually we get a vertical line, and of course, there is a very small resistance in the primary winding. So, considering that, exactly it will be not vertical, but it will be having a little slope, very small slope. So, this is the DC load line. Now, to draw the AC load line, now we consider the AC conditions prevailing, and we know, we have already seen that the primary of the transformer will be having this RL transferred to it by the value RL dash. That is, in the primary winding we will be having a resistance RL dash. So, here will be a resistance RL dash in the AC condition. So, as this transformer primary winding is having RL dash, which is equal to N square into RL, and the load line if we want to draw for AC, then when there is no signal, then the voltage of the collector to emitter will be simply VCC, that is the DC source VCC. Now, when you apply this signal, this is the signal Vs we are applying, and it is a sinusoidal voltage we are applying. So, the current in the collector will be sinusoidally increasing and decreasing. It will be a sinusoidal wave. Starting from DC value, it will be increasing and decreasing. So, that point is Q point, which is the DC point or quiescent point. We know at that point the value of the collector to emitter voltage was VCC and the collector current was, say, ICQ. Now, if we now apply the signal, then the collector current will be increasing and decreasing like this, and when the collector current increases, the collector to emitter voltage will decrease from VCC and it will go down, and the maximum collector current that can flow is at this point where the collector to emitter voltage will be 0, and then it will be again increasing, and in this half cycle when the collector current goes down to the negative half, the AC collector current goes to the negative half, then the collector to emitter voltage will increase beyond VCC and the increment will be to this point, that is the maximum point on the load line, and that point has the voltage of 2 times VCC. Now, why this maximum voltage between collector to emitter becomes 2 times VCC? To understand that, we have to see about the circuit, what it is having in the circuit. We are having a transformer. So, transformer winding carries a current. So, when this current is in the negative half cycle, that means the collector current, if we see the circuit again, if the collector current which is flowing in the primary of the transformer, if it goes down, as soon as it starts falling or decreasing, then the collector current is that factor which establishes the flux in the core. So, if the flux goes down, then due to the Lenz's law, there will be an EMF which will be opposing the very cause behind it. That means, it will not let the collector current to collapse, and for encountering or for overcoming that, it will be actually aiding the voltage by increasing it to 2 times VCC. That means, it will be aiding that voltage VCC, so that it will be preventing the fall or collapse of the collector current. It is due to the Lenz's law. It will be not allowing the collector current to fall, and it will be opposing the very cause behind the fall of the current. So, it will be trying to overcome it, and it will be aiding it by the voltage which will make it equal to VCC, and that is why total voltage at that point when the collector current goes down to the valley, it will be 2 times VCC total. So, the maximum value of the collector current, if we consider the signal, then this is 2 times VCC by RL dash. RL dash is the resistance in the primary winding. So, this 2 times VCC by RL dash will be this peak value of the collector current, and this is equal to this portion. So, VCC by RL dash was here, and the total will be twice VCC by RL dash will be the maximum or the peak of the collector current. And the AC load line is having a slope of 1 by RL dash, but it is in the negative direction because it is, you can see from the load line, AC load line, the slope is negative. So, this is the load line analysis, and what is the maximum swing of the output voltage or collector to emitter voltage from one peak to the other peak. The total swing is 2 times VCC. Now, with this knowledge of the load line analysis, we can proceed to find out what will be the output AC power. So, the AC power, if we consider, we know that the AC power is equal to the voltage and current multiplied, but that voltage and current is the RMS voltage and RMS current. We are finding out the average power, and average AC power is given by IC peak to peak into VCE peak to peak by 8, and that we have earlier found in the class A series fed power amplifier also, and we have deduced that. So, putting down the value of IC peak to peak and VCE peak to peak. So, IC peak to peak means this point to this point is twice VCC by RL dash, and VCE total swing peak to peak is 2 times VCC divided by 8. So, simplifying this expression, we get VCC square divided by RL dash into 2. So, this is the expression for the AC power in a power output maximum. We are considering the maximum AC power output, maximum because we are considering from this point to this point what it can be having. Maximum value of this current can be 2 times VCC by RL dash. So, this is the output power, and the input power, which is a DC power. So, that is provided by the source or battery VCC, and we know that the DC power is equal to VCC into ICQ, and that can be written as VCC into VCC by RL dash is equal to ICQ, because this current ICQ at this point, it is the DC collector current, which is the Q point collector current. Q point is the quiescent point, and at that quiescent point the collector current is ICQ, that is the DC collector current, and that value is equal to VCC by RL dash. So, putting down this value VCC by RL dash multiplying with VCC, we get VCC square by RL dash. This is the DC input. So, now if we want to find out the maximum efficiency of this transformer coupled amplifier, we have to take the ratio, we have to find a ratio between the output AC power and the DC input. So, output AC power P naught AC we have found out to be VCC square by twice RL dash, and this is VCC square by RL dash is the DC input. So, putting down these values, if we find out the maximum efficiency, it boils down to half or 50%. So, here in the transformer coupled amplifier, we achieve a higher efficiency than the series fed class A power amplifier, which we discussed earlier. So, we get 50% maximum efficiency in the transformer coupled power amplifier. Now, this operation of this amplifier, both series fed which we discussed earlier and the transformer coupled power amplifier today that we discussed, they are both in class A operation, because if we look into the output characteristic, I mean the collector current, then we see that the current is flowing for whole cycle, because it is not going down to either saturation or cutoff. So, it is in class A operation, the conduction angle is 360 degree. Now, if we consider another type of power amplifier, depending upon the conduction angle, we have another type of power amplifier which is class B power amplifier. So, in class B power amplifier, we know we earlier got that the conduction angle is 180 degree. That is, the quiescent point is located in such a way that it does not allow 1/2 of the current cycle to flow. For an example, we have a push-pull amplifier which is an example of a class B operation. So, what is there in this class B push-pull type of amplifier? We have two transistors here, they are shown as T1 and T2, and we are having transformer stages both at the input and the output. One example we are showing where we are having a transformer at this input stage and we are having another transformer at the output stage, and the resistance RL is connected to the secondary of the output stage transformer, and the voltage across this RL is V naught, which is the output voltage we consider for driving any load. And here, given an AC input Vs supply voltage at the input, this is a transformer which is having a center tap secondary. What is meaning of this center tap secondary is that we are having actually the same number of turns here on the upper half from this point and the lower half of this point. If suppose we have N1 here, N2 here in the secondary side, then N2 by 2 will be in this half number of windings and N2 by 2 will be in the secondary lower half. That means exactly equal voltages will be induced in the two halves, and we are considering N1 is to N2, that is the turns ratio in this output stage transformer. And we here also we are using a center tap transformer. So, here this is total, if it is N1, this will be N1 by 2, this will be N1 by 2. Now, we note here is that we are having two transistors T1 and T2 which are NPN transistors, both are similar type of transistors, and VCC is the source, this is supply. Now, as we are applying an input voltage which is sinusoidal, what will happen in the positive half of the input? That is, let us consider when we have Vs in, this is Vs in this positive half, let us consider what will happen, how the operation of the transistors will proceed for the positive half of the input voltage cycle. So, in the positive half cycle, this point is positive, this point is negative. Here also we will be having induced voltage like this, that is, this point is the center point is grounded. With respect to ground, the upper point will be positive, and with respect to ground, the lower point will be negative. Equal voltages will be induced here in the both the halves. Now, as this is the case, the transistor T1, as it is forward biased, if we look into the transistor base, NPN transistor this is, so we have this forward biasing for the transistor T1 in the emitter base junction. So, the transistor T1 will be now conducting, and so collector current will flow in the transistor T1 in this direction. Say, let us consider this as I1. But what about the other transistor T2? If we look into the other transistor T2, this is also an NPN transistor, but look at the biasing, this is P is connected to negative. So, it will be reverse biased, there is no conduction taking place in the transistor T2. So, the transistor T1 will only be conducting, and the current flowing in the winding will be I1, and so there will be a current flow in the secondary of the transformer, and this current as it flows, it will be producing an output voltage V0. Now, in the other half of the input cycle, that is in the lower half, if we consider this half, so in the negative half cycle, so what will happen is we get this point positive, the induced EMF will be having these polarities, so that now the transistor T2 is forward biased in the emitter base junction, because P is connected to positive, it will be forward biased, and other transistor T1 will be reverse biased. That is clear from this polarity of the induced EMF here in the secondary upper part, this P, this NPN transistor, so P is connected to negative, so it will be forward biased. There is no conduction in the transistor T1, but conduction will take place in the transistor T2, and so we will be having a collector current in the transistor T2 flowing in this direction. So, through this transformer primary winding, we see that the direction of the current I1 and I2, this is I1, this is I2, earlier it was I1 was in this direction. So, one is this direction, one is the other direction, these two directions are opposite. So, the current which will be flowing by induction in the secondary, which is say I in the secondary of the transformer in the output stage, so that will be the difference between these two currents, because these are opposite. So, it will depend upon the current directions of I1 and I2. So, their difference will be flowing in the secondary of this transformer I. So, here in this type of push-pull amplifier, it is named as push-pull because in one half cycle the current is pushed up and the other half cycle it is pushed down. That is, we are having in the load line characteristic, if we see DC load line, as we have earlier mentioned, it will be almost vertical, and that is because the primary windings are assumed to be ideal, having no parasitic resistance, and that is why in the DC condition the current will be infinitely high, and that is why we are showing it by a DC load line, by a vertical line, and its voltage is VCC is the DC voltage because the source is VCC source. Now, in this type of push-pull amplifier, what we have seen is that one transistor is operating at a time. So, we are combining the operations of two transistors, and finally, we are finding out the output voltage by combining these two voltages which are induced individually by the two transistors in each half cycle. At a time, only one transistor is conducting. So, now if we consider the load line, AC load line, then we are having for one transistor, if we consider the load line, it will be like this. That is, the VCC is the DC voltage, that is when you do not have any signal, when we do not have this Vs, that Vs is 0 suppose, then it will be only having the VCC voltage, that is the DC voltage. That is why it is the DC voltage here, which is the voltage across collector to ammeter when there is no signal. Now, when there is one transistor conducting, say T1, then we will be having increase of the collector current, and the collector current will increase up to the maximum value VCC by RL dash, because that can be seen that we are having this, suppose upper one transistor is conducting. So, ignoring the transistor drop, which is very negligible, we can have only the VCC voltage maximum up to which it can, the collector current can go is VCC by RL dash. RL transferred to this primary side will be RL dash will be N square into RL, N being the turns ratio between primary and secondary winding. So, now if we now consider the load line, AC load line, we are having one point here and the other point is starting point is here. So, this AC load line will be having a slope of -1 by RL dash. This picture is only for one transistor, mind it. So, if we now combine both the transistors and try to draw the voltage and current swings, then for upper portion, when the transistor current I1 is increasing, that means the upper one transistor T1 is conducting, then current is rising, I1 is the sinusoidal current, peak value can be VCC by RL dash starting from 0. This is the AC current that we are considering. And in the other half, when T2 is conducting, that is the current is I2, that is the other sinusoidal current in the other half when T2 is on. So, the load line will be extending to this point, starting from this it will be coming down to here. That means we are having the T2 on is this voltage, T1 on is the voltage will be reducing. So, this is the combination of the two transistors load lines. And if we now find out the DC current which is flowing, because you have to now consider be careful about this point, that we are having a sinusoidal waveform and this is having two halves, one is this I1 and the other is I2. That is why if we find out the total DC current, that will be I1 DC plus I2 DC, and we can find that out, which is nothing but 2 by pi into I peak. The peak value of this current is IP say, then the DC current that will be flowing, the DC value of this sinusoidal current will be 2 times IP by pi, 2 by pi into IP, IP being the peak value of the current. So now if we find out the AC output power, we know that the AC power is not, can be found out if we consider the average AC value, that is obtained by considering RMS, root mean square value. So the output voltage that is obtained across this load resistance RL, because we are interested in this voltage V naught. And what is this voltage? It is a resistive load, so it is current square multiplied by RL. Now that current must be the RMS value of the AC current. Whenever we find out the power average value in AC, we take the RMS value. So I square R, but that I should be the RMS value of the I. So that is why we are writing I RMS square into RL dash. Here actually we are considering the RL dash to be transferred to the primary winding. Everything we are considering in the primary side, because we are comparing, we are going to compare the efficiency etc., the output and input etc., find out the efficiency. So with respect to this input circuit, we will be doing everything. That is why we are transferring this RL from secondary to the primary side. So that is nothing but I RMS square, I root mean square value into RL dash, and root mean square value is nothing but peak value divided by root 2. That is why we are writing IP by root 2 square into RL dash. And if we simplify that, we get IP square into RL dash by 2. This is the AC output power. So AC output power is obtained as given by this expression. Now it depends, that means on the peak value of the current. Now if we consider the DC input, that is what power you are giving as input to the amplifier, if we consider that VCC into IDC, that is the power input, and that is equal to VCC into IDC is we have seen it is 2 times IP by pi. So 2 VCC into IP by pi, that is the DC input. So now if we find out the efficiency of this amplifier, finding out the ratio between the output and the input. Output is the AC output, input is a DC input. Now what will be the ratio between these two? Just by substituting the values of this P naught AC and Pi DC, we get P naught AC is this value I P square RL dash by 2. So we are replacing here I P square RL dash by 2, and Pi DC we have twice VCC into IP by pi. So that is why we are replacing here or substituting here 2 times VCC IP by pi. So now this calculation gives us pi into this, pi will go up, pi into IP, 1 IP will cancel out with 1 IP, and finally what will be remaining is pi times IP into RL dash divided by 4, 2 will come down, 4 into VCC. Now this is the efficiency of this push-pull amplifier. Now if we now consider the maximum efficiency, what will be the maximum efficiency that you can achieve with the push-pull amplifier, then we have to consider the maximum output power and find out the ratio between the maximum output power, which is an AC power, the maximum value of the AC power that can be obtained with the DC input. So in this expression, our variable is, if we look into this expression, the variable is IP, because for a particular push-pull amplifier, the value which is the load resistance that we are fixing, I mean we are not going to change the load resistance, and also we are having a constant DC source. So the peak value of the current, actually this value, it can go up to maximum value is this one, which is VCC by RL dash. So if we put this in this expression, the output power maximum, which we obtain as pi IP RL dash, so pi IP max RL dash by 4 VCC, if we put, just I am writing this again by taking IP max, which can be written down as VCC by RL dash. That means if we now design in such a way that this value IP, which is dependent upon this 2, so you get the efficiency changing. Now if the value of IP, if we now substitute maximum value of the peak current that is given by VCC by RL dash, so what we get is here VCC and VCC cancel, so RL dash and RL dash also cancel, so we get pi by 4. So pi by 4 means in percentage value, if we find 78.54% is the maximum efficiency that we can get for this type of push-pull amplifier. So we have seen earlier that we were able to get 50% maximum efficiency when we are considering a transformer coupled power amplifier. Now here in class B operation, an example of which is a push-pull amplifier, there we are getting an efficiency of 78.54%, that is higher than the earlier cases. And also if we want to find out the power dissipated by the transistor as heat, so this power dissipation can be found out by subtracting the AC power output from the DC power input, Pi DC minus P naught AC. So that will give the power dissipation by the transistors. So that power which is dissipated as heat can be found out by just subtracting P naught AC by P from Pi DC. So putting down these values, because Pi DC is nothing but 2 VCC IP by pi minus output AC power is IP square into RL dash by 2. So if we substitute these values, we get the power dissipated as heat. So in this type of push-pull amplifier, the key point is that we are having class B operation, no doubt. That means for a particular transistor it is operating only in one half, but we are combining these two transistors to get the overall output current, and individually each of the transistor is operating in B mode of or class B operation. So we have seen an advantage is here is that we can increase the efficiency. It is even higher than the earlier examples which we are taking, like a class A amplifier, we were having only 25% and 50% efficiency, but here it is more, which is 78.54%. Now, if we now compare these three amplifiers which we have discussed, that is, we have already discussed a class A and now we are discussing class B. So, from the efficiency point of view, we are having a higher value in push pull amplifier. Now, let us do one example. Determine the input power output power efficiency and the maximum value of these quantities. For the push pull amplifier shown in the figure below. We are to find out the input and output powers efficiency and the maximum values of this input and output power for a push pull amplifier, which is shown here. It is a center tap transformer. Actually, upper half and lower half are having same number of turns. It is having these transistors and we are having a source like this, and at the output side we are having the load RL. So, these are the transistors T1 and T2. This is the source VCC and this is N1:N2 transformer turns ratio. Now, given that VCC equal to 30 volt, you are given that the voltage VCC equal to 30 volt, this RL is equal to 16 ohm, and the turns ratio between N1 and N2, N1 being the primary winding and N2 being the secondary winding, it's 2, and a peak value of the current is 2, not to 1 ampere. So, this is the data given to you. So, now if we want to find out what is the input power, so we know that input power equal to say Pi DC, that is equal to 2 times VCC into IP by pi. So, putting these values, we substitute these values. VCC is equal to 30 volt, peak value of the current which flows in the circuit is given as 1 ampere. So, this is the denominator is only having pi. So, we get 60 by pi, this much watts, and if we calculate 60 by 3.1416, that value will be equal to 19.1 watts. Now, this is the DC input power. If we want to find out what is the DC input maximum, then we will be putting down the IP maximum value that it can have, which is VCC by RL dash. Now, RL dash is the resistance in the secondary, that is the load resistance transferred to the primary side, which is given by N square into RL. Now, here we are given N1 is to N2, this N1 and N2, it is the ratio between the total primary winding and secondary winding. We have to see this. This is the N1 is this total primary winding and this is secondary. So, if we want to find out N1 is to N2 for a particular transistor or for a particular conduction, we will have to find out. So, that is N1 by 2 by N2. So, that will be N1 by 2 means N1 is to N2 we are given, but we will have to find out N1 by 2 is to N2, and if we want to find out, so it will be N1 is to N2 into half, and N1 is to N2 is given as 2, so 2 into half, that means 1. So, RL dash and RL are equal, and which is the value, what is the value of RL? It is 16 ohm. So, now the PIDC can be found out to be just by substituting this 2 into 30 square, VCC into VCC will be VCC square, and divided by RL dash into pi. So, 2 into 30 square divided by pi into RL dash is 16. So, if we calculate this value, it is 35.81 watts. So, these are the DC inputs value and maximum value. So, what will be the AC output? That also can be found out, output power, which is IP square RL dash by 2. IP is 1, RL dash is RL, which is 16 by 2, that means 8 watts, and output power maximum can also be found out. The maximum value of this IP can be found out, which is nothing but VCC by RL dash whole square into RL dash by 2. So, it boils down to VCC square by RL dash, and RL dash 1 will go. So, RL dash into 2, putting these values 30 into RL dash 30 square divided by pi into 2 into RL dash is 16. So, this gives the value of 28.125 watts. So, this we have got. Now, we can find out the efficiency P naught AC by Pi DC. So, P naught AC value is 8 watts and Pi DC value is equal to 35 no, not 35, it is earlier we have found 19.1. So, this value will be 8 by 19.1 and that is equal to 41.89%, and maximum efficiency if we find P naught AC maximum by Pi DC maximum, and these values are 28.125 and 35.81. So, that gives 78.54, which is the typical maximum efficiency value. That also has been verified that this value is the maximum value it can have. So, in this class today we discussed about two types of power amplifiers, which are one is the transformer couple power amplifiers, which are generally used for audio applications, which operates in class A mode of operation, but it is using a transformer to couple the load. And second class of power amplifier that we discussed was a push pull amplifier, which operates in class B operation, and it is having a higher efficiency than class A power amplifier, although it has class B operation in each of the transistor that is being operated, because we are having two transistors and we are combining the operation of the two transistors in push pull amplifier. So, out of all these amplifiers which we discussed till now, we have got that efficiency is highest for the last one that we discussed today, which is the push pull amplifier. And we will be observing later other type of amplifier like class AB also we will be studying later.